Welcome back to my YouTube channel. Today I'm talking about the Rhyper function in R. The Rhyper function generates random values from the hypergeometric distribution. And this is going to look a little bit different from what we've done before. Is now we have 4 required arguments. The first one is in the number of values you want to generate. And all of the other are distribution sampling functions that would be such in, but we already have in the distribution, so we're using in to represent how many we want to pull from the distribution. The m is the number of white balls in the urn, or you could also think of it as the number of white marbles in a bag, or however you want to think about it. With sampling without replacement, we're taking a ball or marble or whatever out, and the white ones are the ones we want in this situation, so that's a success. And so n is the number of black balls, or the choices we don't want to pull from the urn. They're not considered successes. So, or it could be like a black marble. The setup really doesn't matter. Urn feels a little bit unnatural, but that's historically what's been talked about. K is just the number of trials or attempts we make to pull a marble out of the bag. So if K equals 1, even if there are 2 white balls in the bag, we simply can't pull them both out if we didn't pull that many marbles. Okay, so I'm going to go ahead and get started in an example, and hopefully the setup will be more clear. So Rhyper, in, the number of values we want to sample. I'm going to start with 100. M, the number of white balls, or balls we actually want in the bag or urn. I'm going to call that 2. N, the number of black balls, or the balls we don't want. I'm going to say 3. And I want to pull out 1 ball. Okay, so we have 2 balls we do want, 3 balls we don't. So the probability of pulling a ball we want would be 2 divided by all the options. So 2 plus 3, so 2/5, or 0.4. And then, so we have that. I'm going to do this again and calculate the mean. And we get a value somewhat close to 0.4, but I don't think that's necessarily satisfactory. So I'm going to make a huge jump in the sample size, call that 1 million, and we get a number really close to 0.4. Okay? And I also can do the same thing for the variance. R Hyper. I'm trying to reinvent the wheel when I don't need to. So variance. .24. Okay, but what should the variance be? So I pulled the expected value and variance calculation from the built-in R help documentation. So the expected value is somewhat easy to work out. It's the probability times K, the number of marbles you saw from the bag, and that should feel very similar to the binomial distribution, where the expected value is the probability and the number of times you flip the coin. Okay, so variance is a lot harder. And what I did is I took these 2 formulas and I made functions for the expected value and expected variance. let's use these two functions to take my work here. So the expected value, so it to be the 0.4, so m to equal 2, n to equal 3, and k that equal 1. 0.4 naturally. But that's not too interesting, we worked that out in our head. But the variance is a bit more complicated. The expected for this time. And so m is 2, n is 3, and k is 1, and we get 0.24. So that's the variance. And one interesting thing I saw is that even though they're similar setup, the hypergeometric distribution has smaller variance when k is greater than 2. I could definitely see switching between the binomial and hypergeometric when it makes sense. Sometimes the hypergeometric would give lower variance estimates. Okay, so that's not all we can do. We can, of course, go and plot this. Oh yeah. Okay, let's not plot that though. Just thinking of the distribution that way is weird. Let's say we have 20 white balls and the sample 20. Okay, so I named the setup to make the histogram not binary. I didn't think that one through. So now we have 20 possible thickness options, 30 possible failure options, and withdrawing 20. So now we could have a histogram with values ranging from 0 to 20. Okay, that's much better. So it never quite gets up to 20. And that's fine. So the expected value would be 20 over 50. That goes back to 0.4. The probability didn't change. So we have k times 0.4, which would be 8, I believe. So 20 times 0.4. Okay. Let's take that. So expected value m equal 20. If I could type, that'd be great. $30 and k equal 20. Yep, expected value will be 8. And the expected variance I'm going to work smarter, not harder here, would be about 3. It's interesting how when you scale it up by when you scale m and n up by a factor of 10, the probability doesn't change. Which going to make sense mathematically. And then you just have to multiply by k, but the variance is much more complicated with that m n k fractional situation. Okay. So what can we also do? We can do one of my favorite things. Sample. So I'm going to set this up as an vector and arbitrarily name it x. So or a hyper, the number of samples I want to draw. I want 1 million, because I'm about to do a simulation. Okay. I'm going to stay with the setup I had. I probably should have assigned the factory before. Okay, so 20 white ball, stuff I want. 30 black ball, stuff I don't want, and I'm drawing 20. I have a factory. Okay, so we know this histogram centered at 8. And let's see the probability of drawing 10 or more white ball. So what's the probability that, given this distribution, I get 10 or more white ball? That's a reasonable question. So I have a counter variable that I'm going to use to count the number of times we get 10 or greater white ball. Okay? So I'm going to start with a for loop that's going to iterate through each value of x. So what I'm saying is iterate I through 1 to the length of x. Length of x is 1 million, so I'm going from 1 to 1 million. Now I make a conditional statement to find what I'm looking for. So if x of I is greater than or equal to 10, that's a condition. And if it's met, I'm going to say counter equal counter plus 1. Okay, so for each value of x, I'm going to see if it's greater than or equal to 10 and count up. That loop ran essentially instantly. So yeah, to get a proportion, I'm doing counter divided by the number of elements in the factory, so the length of x. And we get that in this hypergeometric setup, there's a 18.7% chance that you would get 10 or more white ball out of the urn, so 10 or more successes. And that can be useful when you're trying to get this proportion here, like a rough estimate. And I find that it helps inform the more rigorous P, Q, and D versions of the calculation, so P hyper, Q hyper, and so on. And it helps confirm that you're in the right tail, because it can be confusing trying to figure out if you're on the right part of the graph, if you need to do 1 minus whatever you got. It does help inform the more rigorous calculation, because doing it by simulation will never give you an exact answer. Even if I did 1 billion instead of 1 million, I'd take up a lot of RAM and time, and it still wouldn't be exact. It would be at some point better to use the exact calculation, but it gets you in the ballpark and it helps you figure out where you need to be. Okay, so that was all I had for today. Thank you for watching.